Hi all. I want to talk about neural networks and universal approximability. So just as a short reminder, if you're looking at this video and you haven't checked the previous video, what is a neural network? You can Google this. Also, it has an input layer. I'm talking about single and variable input. It sends this signal into a bunch of nodes, or thought of as neurons. Each of these neurons fires depending on certain parameters and then sends its output signal to an output that is then summed with certain weights, and that generates our function. Now, our collection of functions is all the functions that can be computed by some architecture like this with some fixed activation function, and what you can change here is the number of nodes and the weights and the variables associated to this activation function. So there's three families of parameters that you can optimize over, say using stochastic gradient descent or some other method. A standard method would be this backtracking method with a single layer, which is essentially stochastic gradient descent. So, but what, in terms of this class of functions, this theorem that was stated in another video is that Fn is dense in the space of all functions. And in that video, I discuss why this is important. This is called the universal approximation theorem, in case you want to Google that and look more elsewhere. So this is universal approximation theorem. Okay. So how do we prove that? There's a small assumption also for going into the proof that we need to make is that, okay, you have to choose a reasonable activation function. And if you use the sigmoid function, I'm afraid that it gets kind of technical and annoying to prove this. So instead of the sigmoid function, I want to use a simpler one. That's a piecewise linear activation function. It performs probably quite similar in practice. It's not smooth, which causes some problems in optimization because you cannot do gradient descent at that. You are close to that parameter point, but okay, let's exclude that now as a small technicality. You could smooth this out if you want. So Sx is defined as this piecewise function, so 0 when x is less than or equal to 0. Between 0 and 1, it's growing linearly until it reaches 1, and then it plateaus. So a signal that's somewhere here will not generate any activation, and if you are a strong enough signal, you'll generate a full thing, and then in between, you'll generate some signal. So this way, at least we have a continuous signal, and this is something that we would like. We need these functions to be continuous, at least to say that they're dense in X, because they have to be a subset of X. This way, they are automatically a subset, because they're sums of activation functions in Sx are continuous. This proof would work with many others, or this idea, but there are some technical modifications for specific functions that you may want to use in practice. Say the sigmoid function that never quite is equal to 0 and never quite is equal to 1. So here you have to worry about what happens very far away. It doesn't turn out to be a big issue because it grows relatively quickly, but it's still something that causes technical issues that would obscure the main points of this proof, and that's why I don't want to talk about them right now. So, okay, what is our task in density? We have a fixed epsilon, and we have to find, so we want to find an F in the neural network, computable by a neural network, so that the distance between F and F epsilon is at most epsilon. But defining this function F epsilon is the same thing as constructing a neural network that will compute Fx up to an error epsilon. So this is our task. Construct a neural network, that is, define how many nodes do we need, and define all the AIs, BIs, and WIs. once we have defined these, then you could code up a simple network that would compute your function. Now, a word of warning, this proof will be very not constructive. It's very non-effective. It will use a ridiculous number of neurons that would be far from practical. Also, in practice, to make really good methods for at least some problems, you want to use multiple layers. So this is in many ways not practical, but it gives you a sense of why this method works and what these neurons actually might be representing in some cases. So it gives you actually a sense of some plausible ways that a neural network actually is able to approximate any function and why it's possible. So it's not completely without merit, even though it is certainly not giving you a practical neural network. Okay, so one thing we need is we need to figure out how many nodes and what each node is doing. And morally, what each node is doing is that we have our interval 0, 1, and each node here is corresponding to a certain interval here. But we need that the function doesn't change a lot in this interval, because essentially we're approximating by one of the endpoints or something very close to that. So therefore, we need to do a little bit, we need to ensure that the function doesn't change over the interval. And the reason for that is that we have a uniformly continuous function. This is the same that you get in 131a when you talk about integrals. So there exists I'll write this now as, there exists a delta such that if x minus y is less than or equal to delta, then fx minus fy is less than or equal to epsilon. Now, because delta is positive, there exists an n in natural numbers such that 1 over n is less than delta. And let's fix such an n. And let's fix such an n and consider the intervals or the partition given by xi equals I over n for I equals 0 through n. So this gives us these points xi. We have x0 is the first one, xn is the last one, and then we have n minus 1 points in between. N intervals, n minus 1 points in between, and n plus 1 total points. Okay, these are define a partition of this space. Okay, how we will do this neural network is that the neural network will actually report the exact value if we are at these endpoints. So how will it succeed in that? Well, it will have n neurons, and the ith neuron, what it will do is that it will compute what is the change in this over that interval. So the weight here, wi, will be f of xi minus f of xi minus 1. So these neurons will be indexed by 1, 2, up to n. So wi will be fxi minus fxi minus 1. And here we will take an activation function that what we want to do is that at xi minus 1, it's 0, and then it grows quickly to 1. Okay, so to get that, what we need is that, remember that our activation function involves a translation by AI and a scaling. Now, this translation corresponds to where we start. So AI should now be xi minus 1, and bi should be equal to a shift that will scale this to have the right length. So 1 over xi minus 1. Okay, so this gives us AI and bi. Now we have to find the number of neurons. We have to find AI, we have to find bi. And we have our neural network. I mean, I define it only for the I, but this formula works for all I. Okay, now what we want to show is that this approximate, let f tilde be the function computed by this neural network. We want to show that this is close to f. I mean, you can test this by a program if you want. I mean, this is all explicit. I mean, you have to make this choice of n, but it works. So f tilde of x, and we want to estimate f tilde minus f of x. We want to show that this has some good bound. Now, let's fix an x in 0, 1. We want to make this estimate, and it turns out that we really want to estimate in between these intervals. So fix an I so that x is in xi minus 1 and xi. Did I miss? We do need one more neuron here, which is defined by so we'll need one more neuron to kind of get the value at f of 0 correctly. So to do that, we will put a weight to be equal to f of 0 is equal to w0. And the activation, it will activate once the value is bigger than or equal to 0. So what we'll do is we'll shift the function just by minus 1, and we'll not scale it at all. This way, what we get is that at 0, we will just add, this neuron will effectively add function value 0. Okay, so there exists an I such that it lies in this interval between xi minus 1 and xi. This I is now between 1 and n. And the idea is, before we actually estimate this, let's first look at cases. If x is equal to xi, I mean, this is only some of these points. It's an endpoint. If x is equal to xi, what is f tilde of xi? Well, f tilde of xi will essentially be, you will always add f0, but then you will get an activating, only the neurons up to I will activate, because the ones after that will not activate. So the neurons up to I will activate. And they will activate with a weight that will be fxk minus fxk minus 1. And what is this? This is a telescoping sum. And this will exactly be fxi. So at the endpoints, these functions agree. So that's a useful calculation just to motivate what happens after that. So if we are between these two values, then, well, f tilde of x is equal to f0 plus all of the ones activating before that. Those will activate fully. Plus, but the kth one will not activate fully now. So what we will get is Si of x and times fxk minus fxi minus fxi minus 1. So this is equal to fxi minus 1 plus an activation function, so something between 0 and 1, times fxi minus fxi minus 1. So now if we look at fx minus fx, then what we get is that this is at most fxi minus 1 minus fx plus the activation function, so plus 1 times fxi minus fxi minus 1. Now by choices, we get epsilon for the first term because these are close by, and we get epsilon for the second term, so we get 2 epsilon here. So if I wanted to fix this proof completely, what I would do is I would choose epsilon over 2 here to compensate for that. But this gives exactly the same value. So f tilde, well, up to the factor of 2, so replacing epsilon by epsilon over 2 in the proof. Is what we want. And the crucial idea in this proof is that, well, we focus on the endpoint first, and in that case, we construct a neural network that has exactly the same value. And the reason is that each of these neurons, what it's doing, it's computing how much does the function change in that interval. And if you have an x here, all of these neurons will activate before and will count the value at that point. And well, if you are in between, it will count some value between these two consecutive points, but it's not too far from either endpoint, and that's why we are close. But that requires choosing an end depending on the continuity and using uniform continuity. And notice that, okay, we use the fact that 0, 1 is compact, so it is also uniformly continuous. Okay, so this proves that a neural network can approximate any function.